is use this expression 1 plus 1 over n raised to the n. We are going to plug in 10 for n. Then we'll plug in 10 squared, which is 100. Then we'll plug in 10 to the third, which is 1,000, and so on. And I want to see, what does this expression 1 plus 1 over n raised to the n equal for each of these values of n? So take a moment and plug those into your calculator and fill out this chart. So the numbers are getting bigger until you get to about 2.718. Do you see how it kind of levels off around 2.718? 2.718 is what we use for Euler's number. Euler's number, if you actually want to know the true Euler's number, it is approximated as 2.718281828, and that pattern continues. So we use approximately 2.718 to estimate Euler's number, E. E is Euler's number. Now, because E is a number, just like pi is a number, you can use this number E kind of like an x. So we are going to start by simplifying natural base expressions. E is called Euler's number. It's also called the natural base. So whether you call it E or Euler's number, you are most often going to hear it referred to as the natural base E. Our first example, e to the third times e to the fourth. We're going to treat this just like it's any other letter. Do you remember our exponent rules? If you're multiplying with the same base, what do you do with the exponents? You add them. So e to the third times e to the fourth is e to the seventh. The next one is 10e to the third over 5e squared. So first, let's look at the numbers. What is 10 divided by 5? 2. E to the third over e squared, we would subtract to get e to the first, which is just e. Number 3, the thing that's missing is a square at the end of those parentheses. When you have a square after the parentheses, you have to apply that square to everything inside. So we have 3 squared times e. What should we do to the negative 4x and the 2? Multiply them. So negative 4x times 2 is negative 8x. Do you remember what happens to negative exponents? So e to the 8x goes to the bottom, and 3 squared stays on top. 3 squared is 9. The next one I'd like you to try on your own. The exponent is negative 3, so it's 2e to the negative 5x, that whole thing raised to the negative 3. Try that one on your own. Times e to the positive 15x. E to the positive 15x will stay on the top. 2 to the negative third will become 2 to the third on the bottom. What is 2 to the third? We're skipping number 5 and doing e to the 2x times e to the negative 5x times e to the fourth. What do you do with the exponents when you're multiplying? You add the exponents. So we have e to the 2x plus a negative 5x plus 4. Combine your like terms. We have e to the negative 3x plus 4. Now, technically, negative exponents move, but do you see how this isn't just a negative exponent? It's an expression. we're going to leave it like this. If I give you a problem like this on a test, I would give it to you as a multiple choice question so you'd be able to see like where you need to stop. Because I don't want to try to confuse you. When you have a square root symbol, you can break this into the square root of 25 times the square root of e to the 10x. What is the square root of 25? Okay, for the square root of e to the 10x, what you basically need to remember is that when you have an index of 2, do you remember how you can change it from a radical into an exponent that's a fraction? So the exponent 10x stays on the top, the index 2 goes on the bottom of that fraction. And now think about what is 10x divided by 2? 5x. So this is e to the 5x. I will likely not give you one of those on a test. I will probably give you problems like number 1, 2, 3, and 6 on a test. Those are the most likely problems that I would put on a test. So if you want to circle 1, 2, 3, and 6, those are likely candidates for quizzes. Really quickly, let's look at number 8. 8 divided by 6, we can simplify that fraction to 4 over 3. And then the e's, we would subtract 2x minus 3. So you can write it as 4e to the 2x minus 3 over 3, or you can write it as 4/3 e to the 2x minus 3. Either way works. If you can find your ln button, which is called the natural log, and we'll be talking about the natural log in the second half of this chapter, there's a reason that e is called the natural base, because it's the base of the natural logarithm. So natural log and e are very tied together. So look for your ln button, you will find your e directly above it. So to calculate e to the second, you would do second button, find your ln button to get your e, and then punch in your exponent of 2 and hit enter. You should get 7.389. Now try e to the negative 0.06 and make sure that you're getting the correct number for that. On your graphing calculator, we are going to graph the function y equals 2e to the 0.75x. So in your y equals button, clear out whatever's already there. 2, second ln to get your e, 0.75x. Notice this particular function does not have any horizontal or vertical translation. It's just a straightforward equation. If you want to see what it looks like on the graph, you can push the graph button. But really what we're interested in is the table, so we can record some values and actually put it on our own graph. So go to your table, second graph button. And you might notice, whoa, those are some crazy decimals. E is a crazy decimal. So if we have a function involving e, we have a function with a whole bunch of crazy decimals. It's typically a good idea to use the values -2 to +2 if they fit on your graph. So -2, we have 0.4. -1, we have 0.9. 0, 2, 1, 4.2, and 2, 8.96. Round it however you want to round it. I mean, when we're graphing, whether you round it to the 10th or the 100th, is it really going to help your graph be any more accurate? No. So -2.4, it's like there-ish and there-ish. This is still an exponential growth graph, so there's still an asymptote. Because this graph was not moved up or down at all, your asymptote is y equals 0. Is our graph above the asymptote or below the asymptote? Above, so the range is y is greater than 0. And the domain, that's the easy part, all real numbers. When we graph number 12, we are going to look at just up to the x. So we have a temporary equation, y equals e to the negative 2x. That's the part I'm going to put in the graphing calculator. Then, the rest of this equation tells us how these points are going to move. What does the plus 1 tell us? And the minus 3 tells us down 3. So let's get our temporary points and then move each of those points left 1 and down 3. When you're looking at your table in the graphing calculator, you can choose which points to use based on what you see in your table. I don't want to use an x value of negative 2 because I can't fit 54.6 onto my graph. So I'm going to start with using negative 1. I'll use 0. I'll use 1. And then at 2, at an x value of 2, that number is so close to 0, screw it, let's not use that number. Let's just use these 3 points. So these are our temporary points, negative 1, 7.4, 0, 1, and something ridiculously close to 0. Those are my temporary points. And each of these temporary points, I'm going to move left 1 and down 3. When we move the graph down, we are moving the asymptote down as well. So our asymptote is at y equals negative 3. You may want to draw in a dashed line to help you see where that asymptote is going to be, because our graph cannot cross that asymptote line. Look at the dotted line. Is it above or below the dotted line? Above, so y is greater than negative 3. The domain is the easy part. If you see the phrase compounded continuously, that means you're going to use this Pert formula, A equals PE to the RT. We set this up the same way we did yesterday. So we're starting with $1,000 times E. Our rate is 8% as a decimal, that's 0.08, times the number of years. Plug it into your calculator, see what you get. You should get $1,083.29. I then put in my calculator using the compounded quarterly formula and got $1,082.43. This is just to show you the difference. So if you compound continuously, you do start to get a little bit more because you're compounding your interest more frequently. All right, let's try 5 years.